All right, thank you. Hi guys, good evening.
Good evening, sir.
Good evening. Just a moment. Okay, so good evening, everyone. So let's get started. So today is our final lecture. Yeah, today is going to be our final lecture. So we're going to wrap up the syllabus today. And yeah. So we're going to wrap up the syllabus today. Just a minute. Of things here. Okay, so fine. So let's look at where we left off yesterday. So that was the factored schemes or approximate factorization. So we are in the concept of solution to parabolic PDEs. Okay, so we're in the concept of parabolic PDEs, and we are looking at the factored schemes. Factored scheme, or also known as approximate factorization. Okay, so what we said was essentially, if you want to solve a multi-dimension problem or solve a parabolic PDE in multi-dimensions, which is partial phi by partial t equals alpha times dou square phi by dou x square plus dou square phi by dou y square. Then we discretize this, let us say, and then we said essentially the memory requirements are very high. Okay, memory requirements are high, so that means phi n plus 1 minus phi n divided by delta t equals alpha by 2 ax times phi n plus 1 plus pn plus alpha by 2 ay pn plus 1 plus phi y, phi n. Okay, so this is what we have obtained, where I have written essentially your ax and ay are discrete operators. Okay, they are discrete differential operators. So what we kind of would like to do in the approximate factorization is we would like to convert this multi-dimensional problem into multiple one-dimensional problems. Okay, because solving one-dimensional problems is much easier compared to a multi-dimensional problem. Okay, so that is the idea. So where ax, ay are the discrete operators, I can write, for example, ax operating on let's say phi as phi I plus 1 minus 2 phi I, okay, comma j plus phi I minus 1 comma j divided by delta x square. Fine. So that is the operator. So this is basically of the length m minus 1 times n minus 1. Okay, so many grid points. That is the length of the operator. Okay. Now we said we want to write this in matrix form. So I want to take phi n plus 1 to the left hand side. Similarly, we want to also take phi n. We want to leave them on the right hand side. Okay. So then because this is a discretization, we have terms like ij, we have terms like I plus 1j and many others, like all the 5 neighbors for each ij. Then this phi n plus 1 is going to be applied for phi ij n plus 1, right? So essentially this is going to show up on the ijth quantity. So that means if you have to write in a matrix form, this will basically result in an identity matrix where all along for 1 1 1 2 1 3 1 4 for all these elements you have phi n plus 1 phi ij n plus 1 coming, and it will be 0 everywhere else. So as a result, my transformed equation of this one when written in a matrix form is going to be I minus, okay, I'm kind of multiplying delta t to the right hand side. Okay, I think it is also important to carry the truncation error, because when we make this change or when we make this transformation, that converting a multidimensional problem into a multiple one-dimensional problems, we don't want to incur larger truncation error than that is already there. Okay, that means we want to only incur the truncation error which could be of the same order as the truncation error that is already there, or it could be higher truncation error, but it cannot be lower than that, because if it is lower than that, it is going to change the order of accuracy of the scheme we are using. For example, you are using a central difference scheme. If you use anything, if you introduce errors which have lower than this truncation error, then they are going to basically erode the accuracy of the scheme. Okay, so this is going to be this was order t square, order x square plus order y square. Okay, do you hear some background noise, or is my voice clear? I think somebody is talking outside. Is it okay, or should I go and tell them to?
It is clear, sir.
Clear only, right? Okay. Otherwise, I can just go and tell them not to speak outside. Okay, fine. All right. So we have, this is the order of accuracy. We have order delta x square, order delta y square coming from these two spatial derivatives. And this is because it is a Crank-Nicholson method. This is order delta t square. Okay, that's what we have. Okay, now I'm going to multiply with this delta t with all the terms. That means even this truncation error also is going to get multiplied with order delta t. Okay, then we're going to get terms like alpha delta t by 2 times ax, alpha delta t by 2 times ay. So this is going to be alpha delta t by 2 times ax minus alpha delta t by 2 times ay. Okay, that is my phi n plus 1. Phi n plus 1. Okay, that's what we have. And then because this is positive, these two will become minus when we go to left hand side. And then on the right hand side, we will have I plus alpha delta t by 2 ax plus alpha delta t by 2 ay. Okay, phi n is what we have. Okay, so this is going to be phi n. Okay, and then plus we have delta t, okay, multiplying order delta t square, order delta x square, order delta y square. Okay, so that is the truncation error that we have kind of there. Okay, so that means the truncation error we have now is actually order delta t cube, and then order delta x square delta t, and order delta y square delta t. Okay, that is the truncation error, the new truncation error that we have as such, because it's being multiplied with order delta t. Okay, now we have not done actually much here. We have just rewritten this form in a matrix form. That's all, the same equations. So nothing new has been done here. But then I will now do something here. So I'm going to write this in a factored form, okay, or in an approximate factorization, wherein I'm going to write this terms as a product of two terms. Okay, so I'm going to write this as I minus alpha delta t by 2 times ax times I minus alpha delta t by 2 times ay, and both operators operating on phi n plus 1. Okay. Now, as you can already see, product of, so this is not equal to this product. Okay, but there are extra terms that are introduced which are not there in this term, right? So essentially what you have is, you have, when you multiply I with I, you're going to get this I. When minus alpha delta t times ax is multiplied with I, you're going to get this term. When minus alpha delta t times this I is multiplied, you're going to get this term. But then you're left with what will happen when you multiply minus alpha delta t by 2 minus alpha delta t by 2 ax and ay. That term is missing here, right? So that is not there. So that means when I write this equal to product of these two, I should also subtract off, because it's going to produce plus alpha. So I'm going to subtract off alpha square delta t square by 4 ax ay phi n plus 1. Okay, so that is what I'm going to subtract off on the left hand side. Now this entire term is equal to what is here. Okay, so that is now equal. Similarly, on the right hand side, I'm going to factor the scheme into I plus alpha delta t by 2 times ax times I plus alpha delta t by 2 times ay. Okay, that is going to give me first three terms, and then again product of these two is going to give me plus alpha square delta t square by 4 ax ay phi n. So I need to subtract off that. That's going to be alpha square delta t square by 4 ax ay phi n. Okay, and then plus we have order. So that plus we have delta t times order delta t square, order delta x square, order delta y square. Okay, so that is the truncation error that we have. Okay, now we have transformed this equation. That means this multidimensional derivative, we made it into product of two derivatives, right? Because now ax is basically discretization in the x direction. Similarly, ay is the discretization in the y direction. Now we made this as a factor, right? As a multiplication factor. Similarly on the right hand side. Okay, but then here although this coefficient is the same, it is operating on phi n plus 1, while on the right hand side it is operating on phi n. So as a result, we cannot cut them off. So as a result, this will be there, but then I can always bring this quantity to the right hand side. So it will basically become plus of this quantity. So I can rewrite this equation as I minus alpha delta t by 2 ax times I minus alpha delta t by 2 ay phi n plus 1 equals I plus alpha delta t by 2 ax times I plus alpha delta t by 2 ay, okay, times phi n, okay, and then I have plus alpha square delta t square by 4 ax ay times phi n plus 1 minus phi n, okay, because this is coming from the left hand side, this is already there on the right hand side, and then you have plus order plus delta t times order delta t, order delta x square, order delta y square. That's what we have. Okay, now this is in a nice shape where we have this is a product of two one-dimensional operators. Similarly, this is a product of two one-dimensional operators. And then if you see here, what we have here is alpha square delta t square ax ay. So this is of the order delta t square times what is the order of accuracy for phi n plus 1 approximated as phi n. This will be also order delta t, right? If you were to expand this in Taylor series, phi n plus 1 about phi n, you will get phi n plus 1 equals phi n plus delta t times dou phi by dou t. That means you are truncating there. So truncation is order delta t. So what you see is that if it is okay if I'm going to neglect this term, because this is of the order delta cube, which is exactly already of the order of order delta t cube that we have, that is arising out of the discretization. Okay, so as a result, I can choose to neglect this contribution of this term, because if I neglect this thing, the error I'm going to make is already commensurate with the error that we already have because of discretization. So we are not introducing a bigger error than that, but we are introducing an error of the same order. So that means we're going to now, with this argument, we're going to now neglect this term, okay, and then we're going to approximate our factorization as only these first two terms on the left and right hand side. So that is going to be, so now our new equation is basically, so our equation is I minus alpha delta t by 2 ax times I minus alpha delta t by 2 times ay pn plus 1 equals I plus alpha delta t by 2 ax times I plus alpha delta t by 2 ay times phi n. Okay, So this is the problem we have recast into. This is the approximate factorization. Okay. Now, it is not very clear from this statement, like how is it actually better than the previous statement we have written, which was this, right? So how is this better? So to do that, we are going to look at now how we go about solving this thing. But we have already seen yesterday that if we want to solve this equation, you essentially end up with a block tridiagonal matrix algorithm or a pentadiagonal matrix algorithm or something like that, so that you can solve this. So this is going to be of very large memory requirements. We said this is going to be of using 10 power 8 elements if you are dealing with a 101 by 101 system. Okay, fine. So then how is this going to be better? This is going to be better in a sense. So what I'm going to do is that now everything on the right hand side is known. So let us call this as sum f bar, okay, because this is all known. This is all in terms of phi n. Okay, then let me call this entire vector as some z bar. This is basically this matrix times this phi n plus 1. So then what I'm left with is I'm left with I minus alpha delta t by 2 ax times z bar equals f bar. Okay, so this is going to be I minus alpha delta t by 2 times ax times z bar equals f bar. Okay, so if I were to discretize this, what will be that? Essentially, this is going to be, if I were to write in index notation, this is going to be z ij minus alpha delta t by 2 times, if I apply ax operator on z bar, that is going to be zi plus 1j minus 2 times zij plus zi minus 1j divided by delta x square equals fij. Okay, and then our I goes from 1 to all the way to m minus 1. Our j goes from 1 to all the way to n minus 1. Okay, so that is what we have. Fine. What kind of a system is this? This is basically, if I were to write minus alpha delta t by 2 delta x square times zi plus 1j. So the zij I'm combining with this. That's going to be plus 1 plus alpha delta t by delta x square times zij, and then I have minus alpha delta t by 2 delta x square times gi minus 1j equals fij. Okay, so this is basically leads to a tridiagonal matrix, right? This is leads to a tridiagonal matrix. You have non-zero quantities here, here, here. Then this is z, and then this is your f. Okay, so that's what we have. That means I have to solve this tridiagonal matrix for each j. That's all. For each j, I just need to solve this because we already said f is known. So we just need to solve in x direction for each j, right? So that's what we will do. So once we have solved this thing, we're going to get the z vector. Okay, once you solve this, you're going to get z vector. So this is much simpler to solve because this is only, you have to solve m minus 1 equations, you know, n minus 1 times, right? Isn't it? Because you have to solve it for each j, you will get one such equation. So that means you have to solve m minus 1 equations n minus 1 times. That is much easier than actually solving m minus 1 n minus 1 times m minus 1 n minus 1 matrix. Okay, so this is only going to be m minus 1 by m minus 1 system. Okay, and then we have to do it n minus 1 times because we have to do it for each j. Okay, fine. That means you have to do 100 square. That means 10 power 4 equations only we have to solve. Of course, we have to solve it 100 times. Okay, so that's going to be only in millions, right? It's going to be in only 10 power 6, not 10 power 8. So it is 100 times slower or 100 times lesser, computationally less demanding than the previous case. Okay, fine. So then once you have z, I can go back and then use this equation itself, that is I minus, so use this equation, z equals this thing, so that is I minus alpha delta t by 2 times ay of phi n plus 1 equals z bar. Okay, so that means if we have to discretize this, we're going to get pij at n plus 1 minus alpha delta t by 2 times phi I plus 1j at n plus 1 minus 2 phi ij at n plus 1 plus phi I minus 1j at n plus 1 equals zij. Okay. Okay. Oh, I missed something. Okay, divided by delta y square. Okay, it cannot be I minus 1 because we are applying ay operator. So this is I j plus 1 minus 2 phi ij n plus 1 plus phi I j minus 1 n plus 1. Okay, so that's what we have. Okay, that means what would this be? This would again be minus alpha delta t by 2 delta y square of phi I j plus 1 and plus 1, plus we have 1 plus 2 gets cancelled in this case. So this is going to be alpha delta t by delta y square phi ij and plus 1. And then we have minus alpha delta t by 2 delta y square phi I j minus 1 and plus 1 equals Zij. This was already obtained. So you have to now solve for another tridiagonal matrix algorithm. But then this time you're solving in y, right? Because this is in y. So this is going to be n minus 1 by n minus 1 system in which you will solve for phi on the right hand side is z. Okay, this is now obtained. Then you will get what are the phi values. Okay, you're going to obtain what is phi n plus 1 at all the grid points. Okay, so again you are solving n minus 1 by n minus 1 system, PDMA, m minus 1 times. Okay, so this is much simpler than actually solving the full matrix. Okay, so of course this can be extended to 3D as well in terms of solving. Okay, the approximate factorization can be extended to 3D. So approximate factorization can be extended to 3D as well. Okay. Okay, how do I do that? In 3D, you're simply going to get I minus alpha delta t by 2 ax times I minus alpha delta t by 2 ay, I minus alpha delta t by 2 az, phi n plus 1 equals essentially the same thing, I minus alpha delta t by 2 ax, I minus alpha delta t by 2 ay, and then I minus alpha delta t by 2 az of phi n. Okay, so that is how we could do in 3 dimensions, right? That means you're going to solve 3 series of 1-dimensional problems instead of one big problem. Okay, I think here it is much more bigger problem, right? Because you have 10 power 4 elements here and 10 power 4 elements here and then 10 power 4. So it's going to be, 10 to the power 12 system, right? So it's kind of much bigger. Fine. Okay. Fine. Is this clear what we are trying to do in the factored scheme, the approximate factorization?
Yes, sir. We will check and come back.
Okay, fine. So, okay, so we have looked at the approximate factorization scheme. Then there is a very close equivalent of this, which is known as in the literature as an alternate direction implicit, alternate direction implicit method, which is known as the ADI method. Okay, this was proposed way back in 1955 by Peaceman and Rochford. So this method is kind of can be shown to be equivalent to the factored scheme. Okay, to the factored scheme or approximate factorization. Okay, it is equivalent, but then it was proposed in a slightly different way. But then this scheme is under the general solution methodology of what is known as fractional step methods. Okay, in which in which different terms of the PDE are advanced using different time stepping schemes. Okay, what does this mean? That means this is very much used in numerical solution of PDEs. So let us say if you take a general PDE that applies to fluid flow, let's say you take Navier-Stokes equations and so on. What happens is that you have several terms. Essentially there are several terms. Now you may choose to pick one particular discretization for certain terms and then something else for the other terms. Now, why do you want to do this thing? You want to do this. Sometimes, let us say you have several terms, and then what happens is that, let us say the terms 1 and 2, and I have 3. Let us say the terms 1 and 2 do not impose a very large time step restriction, whereas term 3 imposes a very large time step restriction if we had used explicit method. Okay, so as a result, what we do is that because a very small time step restriction is coming from the terms 3, you choose to solve term 3 using implicit method, whereas you choose to solve the other terms using explicit method because it is going to reduce your memory requirements. That means, but you are advancing with the same delta t. But then you say, okay, now these terms 1 and 2, I would like to discretize using explicit Euler, whereas these terms I want to discretize using implicit Euler. So that is how you can do, and this is very much used in all software in terms of what you want to pick as implicit and what you want to pick as explicit. Okay, which terms? Now that is exactly the motivation for alternate direction implicit method. As the name suggests, we are going to do implicit method in a particular direction, and we're going to alternate it. That means in one step we're going to do implicit method in certain direction, and then choose the other direction as explicit, and then after that step is done, in the next step we're going to reverse these roles. Okay, we're going to change the explicit to implicit, implicit to explicit. Okay, so for that, let me go back to this two-dimensional parabolic equation, that is dou phi by dou t equals alpha square times dou square phi by dou x square plus dou square phi by dou y square. Okay, that's what we have now. Instead of going from, so we want to go from t to t plus delta t. Okay, in one step. So instead of doing this thing, we go in 2 steps. What do? We go from t to t plus delta t by 2. Okay, and then we go from t plus delta t by 2 to t plus delta t. Okay, so we choose 2 steps. One from t to t plus delta t by 2, then t plus delta t by 2, t plus delta t. What do we do in the first step? In the first step, we're going to choose or discretize dou square phi by dou x square term using explicit Euler. Okay, and then we discretize the dou square phi by dou y square using implicit Euler. Okay, and then when you advance from t plus delta t by 2 to t plus delta t, you're going to reverse these roles. You're going to say, I'm going to choose dou square phi by dou x square using implicit Euler, and then dou square phi by dou y square using explicit Euler. Okay, so now what is the advantage? The advantage is that when you consider implicit Euler only in one direction, either in y or in x, you are going to build a matrix, a TDMA, only in that direction. That means these guys will be left over on the right hand side because they are all known in the explicit Euler, they are all known at the nth time level. Okay, whereas these guys, because they are implicit Euler, they will be unknowns and they are required at n+1 time level. So as a result, they will go to the left hand side. And then when you reverse the roles when you go from t plus delta t by 2 to t plus delta t, this is going to be implicit Euler. So you need this at the n+1. Okay, I'm using n+1, but ideally this is n and n plus, yeah. So let me leave it here. Okay, but then we will write the correct equation a little later. So this is going to build a matrix, right? Whereas this one will be known. Okay, so this will be known. This will basically build a matrix. Correct? I think that idea is clear. Then I'm going to write the discrete equation. Okay, the corresponding discrete equation for the parabolic equation is nothing but phi n plus half minus phi n divided by delta t. Okay, so we're going in two steps: phi n to phi n plus half to phi n plus 1. So this is going to be alpha, and then we're going to discretize dou square phi by dou x square using explicit Euler. Using explicit Euler. So we need n values, and then dou square phi by dou y square using implicit Euler. So we need these values at n plus half. Okay. So as you can see, we're going to n plus half. This is required n plus half. This is at n. This is n. So that means these terms will go to the left hand side and they make a tridiagonal matrix. Okay. So they basically make a TDMA matrix. Okay. Similarly, in the next time step, when you go from t plus half delta t to t plus delta t, we will have phi n plus 1 minus phi n plus half divided by, so this should be delta t by 2. Okay. Yeah, this should be delta t by 2 because we're going it, half as such. And this is going to be alpha dou square phi by dou x square at this. We want to make it now implicit. So as a result, this is at n plus 1. And then you want to make the next one explicit. So explicit here is n plus half because the previous time level is now n plus half. So as a result, this will stay at n plus half, where here n plus half means it is implicit, whereas here n plus half means it is explicit because you are going from n plus half to n plus 1. In the previous case, n plus half means it is implicit because you are going from phi n to phi n plus half. Okay, so that is how you do it. So then, as you can see, this is very much equivalent to what we have done in the approximate factorization. This is slightly kind of this thing. Okay, but then again, you realize that means if you have a domain. So let us say that is the domain. Okay, so okay, I think let's push it. Okay, let me see. Hopefully it will do. So we have a domain, something like this. Okay, so that's what we have. We have this domain, and then what we're trying to do is that you are solving implicit Euler in one direction. Okay, so this is all implicit, and when you go, so when you're solving in the implicit this direction, the other values in the other direction are explicit, right? So that means you're only solving implicit in this direction. Okay, when you're doing it the other direction, okay, in this direction, you're doing essentially implicit in this direction. Okay, so that is the idea. So that is the idea of the ADI scheme. Okay, now the same concept can be also used instead of in parabolic equations, even in elliptic equations, the same concept can be used in elliptic equations. When you want to solve using, let us say, a Poisson equation or something, then we call this as line by line tridiagonal matrix algorithm, in which what you can do is you're going to use your TDMA in this direction, and when you need points in the other direction, these points you would use in a Gauss-Seidel format. Okay, Gauss-Seidel or Jacobi format, where you're going to use directly those values, but you're going to build the matrix for in the x direction, okay, or in the y direction. So that will be your kind of, you do this. Although the problem is 2D, you're going to do 1D problem. That means you're going to solve along a line, and everything that is required on the other sides, you're going to basically take it as explicit. So let me put this one. So if you remember, we had this discretization, right? In an elliptic equation, we had basically phi I plus 1j plus phi I minus 1j plus phi ij minus 1 phi ij plus 1 minus 4 phi ij equals delta square fij. Okay, that's what we have. That means how we are going to solve this. So as we said, if you want to solve this, you need a pentadiagonal matrix, right? But then instead what you do is that, okay, let me first solve in x direction. So that means I'm going to take all my unknowns in the y direction as known values. Okay, so let's say known values, we call it star. So we're going to send the known values to right hand side. So my matrix is going to be phi I plus 1j plus phi I minus 1j minus 4 phi ij equals delta square fij minus phi ij minus 1 star minus phi ij plus 1 star. Okay, so you will solve like this. This is only a tridiagonal matrix, right? It's just a tridiagonal matrix, and you will solve this for all. So you will solve it along a I line, right? Along I line, you will do it for all j, right? Because this will form a matrix along all I values, and you would solve it for all j. That means you would solve, you go like this, right? You solve here, 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 TDMA. Okay, and while you are solving that, the ij minus 1, ij plus 1, that means these values that are required, when you solve this value and this value are required, these values you're taking them as whatever is already available, right, from the previous iteration. Now, once you solve it, let us say you solve it from bottom to top, then you solve from left to right. So when you solve from left to right, you change the problem, right? You want to construct it as essentially, you want to now denote these two as star values or known values, and you want to include these two values as unknowns. That means you want to write it as I j plus 1, I j minus 1 minus 4 phi ij equals delta square fij minus phi I plus 1j minus phi I minus 1j. Okay, so these, let us put star values. That means whatever is there, that is what you're going to consider. That means when you propose a TDMA in this direction, right? So when you propose TDMA in this direction, you're going to consider the values of that you need from I plus 1, I minus 1j, I plus 1, I minus 1j. These you will consider that they are known. Okay, and then you will solve for a TDMA in this direction, right? So you would solve for TDMA in this direction. Fine. So that is basically, when if you want to apply to a parabolic, an elliptic equation. Okay, and this is what if you want to do it for a parabolic equation. Both are very much equivalent. Only thing is that here you have time stepping, which will basically give you this phi n plus 1 and phi n plus half. In elliptic equation, you don't have the time stepping, right? So as a result, you are working with this so-called iterations, right? So you're only working with iterations here. Fine. So that is about the alternate direction implicit and the approximate factorization. So that essentially finishes the entire syllabus, whatever we wanted to learn in this course. Okay, so if you have any questions, you can ask me now, or you can even contact me later through email, me or the TAs. But before we close, I want to quickly show you the next assignment as we discussed, which is coming up. Okay, let me just share the screen. Okay, do you see my do you see the assignment 5 here?
Yes, sir.
Okay, so assignment 5. So what we have is, so I made sure there are no programming assignments. So I will post it today. So you will get some 10 days to work on it. It is very simple, actually. You can probably finish it in a day or two. So I put a tentative date of December 15th for its submission. So the first problem is classify the following second order partial differential equations as either parabolic, elliptic, or hyperbolic. Using the b square minus 4ac test that we have learned in the class. Okay, so you would use that test and then see whether each of these equations is parabolic, elliptic, or hyperbolic. Okay, that is very straightforward. You would work with that. Fine. Then the second problem is basically given a steady state temperature field, that is dou square T by dou x square plus dou square T by dou y square equals x square plus y square. Okay, so here x and y are the coordinates of these points. Okay, so we said domain extends from 0 to 4 and the grid is uniform. That means this point here is 0, 0. It goes from 1, 2, 3, 4. Okay, that means each of these coordinates is 1, 2, 3. Each of these coordinates is 1, 2, 3. Okay, so that is the delta is 1. and delta x equals delta y equals 1. Now obtain the difference equations for the interior points using second order central differencing in both x and y directions, taking the boundary conditions into account. So I asked you to calculate what is the obtain the difference equation. So you will write difference equation for the interior points. Okay, all the 9 points you will write the difference equations. Wherever you need to use, let's say, a left point, if it happens to be boundary, you would use 300. If it happens to be right boundary, you would use 400. When this point is discretized, if you have to use both 375 and 400, you would use them. Similarly, when you are here, if you want to use ij plus 1, ij minus 1, or ij minus 1 and I plus 1j, you will use 375 and 400. Okay, that's what you would do. And then once you have all the equations, that means you have 9 equations and 9 unknowns. I asked you to just perform one iteration of Jacobi and one iteration of Gauss-Seidel. So remember, when you're doing Jacobi, you are not updating the right-hand side values. All the values are at phi n, and then you would use that. When you do Gauss-Seidel, you would update the values with latest values that you have obtained. For example, you're starting with an initial guess of 325. When you come to evaluate this location, you will use the just updated value of 325 in the Gauss-Seidel. Okay, whereas in Jacobi, when you calculate 350, you will still use 325 only. Similarly, when you come here, in Jacobi, you will still use 325 and 350 as these values, and these values as 350 and 375. Whereas in Gauss-Seidel, although you will use 350 and 375 for these points, you're going to use the updated value of I minus 1j and then the updated value of ij minus 1. Okay, and then you would perform one iteration, just one iteration. It's going to be simple calculation. Okay, for each method, begin with an initial guess that is shown in the figure. Fine, I think this is very straightforward. Then, okay, I put in programming for those who are interested in, kind of learn to, essentially wants to code, but I put this as optional, so it doesn't carry any points. So I just said, try coding this problem on a general n by n for an initial condition. And you can begin with, 10. And once you confirm your code is running correctly, you can then increase the grid size to 50 by 50 or 100 by 100 and obtain results. You can plot the variation of temperature versus x or y on the central lines. That means you can plot how does temperature change as a function of y on this central line. Similarly, how does temperature change as a function of x on the central y plane. Of course, in each case, you need to iterate till convergence. So you have to put where your Tn plus 1 minus Tn in some norm is less than some tolerance. Okay. The convergence criteria can be defined as unchanging solution between any two iterations as this thing. Okay, so 2 should have been below. Anyway, I'll change it. This is L2 norm. You can set it as 1e minus 3, and then you can stop the solution once it converges to that value. Okay. Yeah, I think that's all. There are only 2 questions. Very straightforward, actually. Okay, you can finish in probably a day or 2 and then submit them whenever you get a chance. So that brings us to the end of this course. And as promised, I will give you some problems, practice problems from the last 3 chapters, maybe 1 or 2 from each chapter so that you can practice. And then look forward to your assignments. Okay, I'll also get them graded. I think assignment 2 was already graded. 3, 4 also will get them graded, and then 5, whenever you submit, we will get them graded and return it to you. Anyway, I think after the deadline, I'm going to post, I'll anyway post the solutions for assignment 3, 4 also, so you can verify your answers compare with the correct solution. I think most of you are anyway getting correct solution, so it should be okay for you. Yeah, so I think that finishes the course. If you have any questions, you can ask me now, or you can email me later. Okay, so that's the idea. Well, yeah, I mean, it's nice, wonderful to teach all of you. I hope you have learned something in this course. Hopefully, a good amount of programming and then numerical methods. I hope it will be useful to your work, whatever you're doing later on. I'm sure, whatever you're doing, either in solid mechanics, fluid mechanics, or in controls or anything, numerical methods is an integral part of all the work you carry out. So you will definitely, cross paths with numerical methods at some point, and then I hope it will be useful. And yeah, so I think it's been a great semester for me to teach numerical methods to all of you. And I also nicely learned some MATLAB and then programmed and then shown it to you for you only, because if I teach on campus, I'm not coding a single line. I want all the code should be written by students and not in MATLAB. Usually it is in, C or Fortran. But then only for you guys, I kind of made sure I write some codes and motivate you so that you can do it. Okay, so I hope you like the course. I have enjoyed it, and I hope you have enjoyed it as well, as much as I have. And maybe I'll see you, sometime when you work for your project or when you graduate on the graduation day, or whenever you come to campus, you are welcome to come by my office and say hi. Okay. So with that, I'm going to stop here, and maybe if there is any feedback that you have to give for the course, if there is any feedback form that will be circulated by code office, I request you to please do so that I can. Yeah. You have already given, is it?
Yeah, already.
Oh, I see. Okay, fine. If you have given, thank you very much, because that way maybe I can improve the course and also maybe my teaching with your feedback. And then if there is anything that you want to say now, you can say. We can also take maybe a picture. Maybe if everybody can, switch on their camera, whoever has it, then maybe we can take a good picture. Once everybody, but then one of you have to send it to me, because I think my picture is also coming, so no problem. We can take it. I can take a picture. Yeah. So it's nice. Yeah, good to see all of you. I mean, throughout the semester, you only saw me. I never saw you. I could only hear two people speaking, 2-3 people, either Arunachalam or Chidambaram, or sometimes, a few others. Yeah. Yeah, good. Okay, so shall I take a picture now?
Yes, sir.
Yeah, let's see.
Yes, sir. Please go.
Yeah, let's see. I think hopefully. Okay. Yeah, I think. Okay, I've taken one. Let me take one more. If one of you also wants to take, you can please take and email it to me, just for safe side. Okay, I've taken 2 pictures. Can probably save it. Okay, so I'll save it. Okay, so I think it'll be here, so not a problem. I'll take care of it. Yeah, so one second. Oops. Just want another screenshot, hopefully. Yeah. Okay, save to desktop. Okay, fine, good. All right. Thank you, guys. We are done. Yeah, so that's all. I'll inform the code office that we are done with the course. I will make sure all these lectures are up there. Okay. Yeah.
Thank you, sir.
Sir, thank you, sir. Thank you so much.
Thanks a lot, sir.
Thank you. Thank you very much.
Thanks.
Yeah,
Yes, sir.
excellent.
It was.
So
Yes, sir. It was.
yeah, so
It was sir, a great learning experience with you, sir. Like, yeah. So we had that both feeling, like subject, like theoretically as well as practically, when means how to implement that in MATLAB, and like how it comes to the physical world. So it was a great learning experience, and you have been quite generous in midterm. So we
sure.
expect that.
No. I mean, yeah, finals also will be similar. Okay, it will be a little bit tough. Not in a sense. I mean, I'm not saying tough to scare you off. I just want the spread to come. There will be questions which everybody can answer, but then depending on your preparation level, you will be able to answer better or something. Because I just want you bring some kind of spread among you. As you understand, I can't give A grade to all of you. That is the thing, right? So,
Okay.
so some spreading should come out. Unfortunately, in midterm it didn't come. So hopefully it'll come. Yeah.
For 2023 batch, it is the last course. These are the last courses. So
I
we
see.
expect for us, yeah.
Sure.
We will go happily, sir.
Sure. Yeah. Good. So, but do you think it would have been so? I mean, all the while I've been writing on this pad. Do you think it would have been better if I had used slides or something, or these?
No,
this
sir.
better?
No, sir. It is better, sir.
It is
We
better.
could follow
sir, you
Yeah.
sir is writing on the.
Sure. Because I like to write
Sure.
only on the blackboard, I know, or on this one, because that puts the pace. Otherwise, I can just finish the entire syllabus in 2 weeks. If you
Yes,
put
sir.
slides.
One thing, yes, sir. One thing, came to my mind just now. So, Sankaran sir also used to teach the same way, writing on the pad. And additionally, he added one thing, flip learning. He used to give us the videos one day in advance so that we could watch and then come to the class prepared. So, and the class run through much quickly. So
Hmm.
maybe that will help even better to like.
Right. So
And
essentially, what I'm going to teach next, I will give you some material, which you will prepare and come.
yes, sir.
Yeah. Sure. Yeah, this is something on my mind. Maybe I should make some lecture notes together with while I teach, so you can read the lecture notes and come. Maybe that is something I should do. Lecture notes
Right.
need not be in a PDF format. It could be in a web-based format where you kind of click and then learn those things. Some kind of an interactive lecture notes. I'll think of it. There was some initiative which I attended where we build Jupyter notebook kind of textbook or lecture notes, which is a little bit more interactive, but only thing is that it'll take a lot of time for me to type up all those things. I have to come up with nice way of putting in, the snippets on all those things. But I'll definitely try. Maybe I'll start with the lecture notes first, and then do it this way.
Sir, one suggestion is you can use this session's videos, sir, or this year's videos for the next year, which will be helpful
Yeah.
to the other batches.
Sure. Yeah.
Sir,
Yeah.
he never makes any data or anything in specific. What Shankaram sir used to do is he gives exactly all the videos of the previous year to us. So
Okay.
he says,
Yeah.
so no extra efforts he does basically. So as what Vivekanand says, you just transfer these videos in
Right.
so that they are going to see the first video and then come tomorrow
Oh,
for
hello.
class.
Lecture.
Like this.
Okay.
Yeah.
Sure.
So you
Excellent.
don't have to- and definitely your tab works mainly for this subject, sir, because slides are not going to work for numerical.
Yeah, exactly. I mean, we can see. I mean, making slides will take a lot of time, but then once you make it, you're done. But the thing is that once I put up slides, I will also forget. You will also forget, and nobody remembers anything.
Exactly.
Yeah.
This is very
Right.
interactive for us, sir. This is very
Yeah. Yes,
Actually,
exactly. Good.
really appreciate your effort in putting this, sir. It was very meticulous and very structured and very useful, and it was very interesting for us, sir.
Sure. Yeah. Thank you, Vivekananda.
It takes a lot of effort, sir. I think like whatever you have means on all the classes, it takes a lot of efforts. And thank you for
Yeah, sure.
thank you for
Excellent.
your efforts. And
Yeah, excellent.
we got to learn like a lot of things, including the MATLAB and
Yes. Yeah.
And thank you for your support in getting
Definitely.
that.
I think MATLAB will be very useful for you. Whatever you do, because it has now integration with Python and everything. So I think it will be very useful. Either later on, if you want to build on the toolbox that is there, Simulink, other things, I think MATLAB will be very useful. Yeah.
Sir, one suggestion for the future batches, sir. It would be
Sure.
better if, because the subject honestly is a bit heavy, sir, as compared to the other ones.
Correct.
For us, doing now along with our main projects is kind of getting difficult, sir. And on top of that, code started this semester on the 8th of September. So it's basically a crunch happening in 3 months altogether. We had recently our 0th review also last week for the project. So instead of having course, because CME is a core subject, so better if this can be given even in second year, like it might be a bit of a relaxation for the students when they are going to do at the final year. Like now, how the 2024 batch students are doing, they're pretty much comfortable, I would say, compared to what we are right now. So that's one thing, because we have failure analysis also is another kind of heavy subject. This one plus the project, so it's like kind of getting accumulated. That's one.
Right. Sure. So I'll inform. We'll make sure that this course comes in the second semester, so that it'll become. I think for some reason they had some thing where they couldn't run it for you guys. That's why probably they have to combine. Yeah.
Okay, sir.
Sure.
Yeah. Thank you, sir.
Thank you.
Yes, sir.
Sir, regarding formula sheet, shall we send it on Monday? Or?
Correct. Yeah. So can you send me by, let us say, Monday? Is it okay?
Yeah, Monday.
Sir, till we complete the assignment 5, can we take some time, because we'll also get used to it. we'll know what.
Yeah, correct. No, I agree with you. See, the only constraint I have is, I'm supposed to give the question paper, already to the code office for your exam because the exam is conducted by some third party, so they have to follow their own time restrictions. So that is the reason they are pressurizing me to give the question paper, which I have kind of resisted till now, which I'll resist for a few more days, maybe, until next week or something like that.
Fine, sir.
Okay. I mean, there is also some personal thing, I have not really set up the question paper because, I am teaching and I'm grading the other course I was teaching on campus. But maybe if you can give some time by next week, Monday or Tuesday, but don't worry, if you want formulas for the later part, you can type it up from, this thing, or I'll probably give you the formula also. See, I mean, the thing is that I don't want to give formulas in the question paper because I may ask you to write the formula because that might carry some points, so that is the reason I don't want to give too much things in the question paper, because if I write the formula, you will not get any points for that. You will only get points for numbers, when you substitute numbers and calculate. So that is the reason. Yeah, so you write as much as you want in 2 pages, and then by Monday or Tuesday, if you can give me that formula sheet, I will put it together with the question paper and then roll it up.
Sure, sir.
Fine, sir.
Okay. Yeah. I mean, you use whatever font that is visible to you, because it will be printed. So,
Sir, right now,
yes.
what we are planning is that we are just whatever in the class you have given whatever writing, same thing we are snip it and paste it, sir. That will be better.
Sure. Whatever way, if you feel that is okay, you can all read and understand, you do it, not a problem. It need not be typed up. It can even be copy paste, whatever, whatever way you want.
Sure.
Okay, just make it little bit looking nice so that when people distribute, they should not look at it like, okay, this is some haphazard text or something. It should be somewhat systematic. So you just make it like a table or whatever. I think make it something nicely and then just give it to me. Should be okay.
Sure.
Sir, it will be an online, sir.
It will be an
Online exam wherein we have to go to centers like TCS. So we given computers where the question paper will be displayed, and we'll use those question papers to write. So PDF will be displayed. That PDF you'll have to read and then write the answer sheet.
Oh, I see. It will not be a printed thing, is it? Okay, it will be an online question paper.
No hard copy, sir. No.
Oh, I see. Only your answer sheets will be the physical answer sheets.
Hard copies.
Oh, I see. Okay. Fine. Then it is fine. Not a problem. Yeah. Then it should be fine. Yeah. So I'll set something like 6 or 7 questions, depending on the time. And then it will be lengthy. So see how much ever you can answer. Fine. Anyway, the grading will be relative. So that should be okay. I mean, don't get stressed out about the exam. Just follow, this thing. That's all. Don't think about all the 7 questions, 6 questions. You also have 3 hours. So just, keep that composure and then answer it. Okay. Yeah. You also remember that you don't have to answer the same order. If you feel some question you are very confident you can start with that, you start with that question. Okay, because a lot of times your strategy of solving question paper also gives you, better points in terms of, because you'll be able to solve it better. If you start with the question in the same order, first question is tough and you see, oh, no, I have made a mistake, and your mood will be like, second question also will go. So you think of all those things and then give the attempt. Okay, it should be fine. I think all of you will definitely pass. I'm looking at how the spread will come and, who will be the topper and all those things. That's all.
Yes, sir.
Okay.
Sir,
Or there will be some innovative ways of answer. Yeah.
Sir, considering you have still not set the paper, and if you can, and also considering the exam is just on the next day of our FAD's exam.
Correct. Yeah.
Because sir, if it is in IIT campus, at least we can reach a bit faster. We don't even know in which college you are going to write. So just help. Though it's lengthy, it's fine. Just complications part, you please help us out.
Sure. Yeah. No. So complications in a sense, I will make you a little bit think on how to solve this thing.
That's
okay?
fine.
So it will not be, of course, it will not be impossible, because see, if I give you a paper which you can't solve, then it is not a good question paper. But you should be able to think about it, and then even after the exam, maybe if you have not attempted, you should be able to think about it.
Yes.
It should be something like that from whatever is taught. It will not be out of syllabus question paper.
Sure, sir. Thank
okay,
you.
It will be from the same thing, but it could be in a similar lines.
Sure, sir.
Let us say if I taught you bisection method, I will invent some other method which is like bisection method, maybe. Then you can think about it and tell, okay, maybe this is a better method, something like that. Okay,
sir. Thank you, sir. Thank you, sir.
Thank you. Yeah.
Yes, sir.
Sir.
Okay. All right.
Thank
Yeah.
you.
Anything else?
Midterm answer sheets corrected paper. You can.
Yeah, midterm answers you want correct. I have the actually shared the corrected answer sheets. I don't know whether they'll share you each an individual or not, or if they're going to give you the scores. Will they give you the scores?
Yeah, they share the course, sir.
But do you want the graded answer sheets?
Yes, sir.
Okay. I'll see if they can email you. Otherwise, what I'll do is maybe I'll ask my TAs to email you one by one. It'll take a little time, you know, because there are some 30, because I don't want to share all the answer sheets with everybody. That is a kind of, you know, privacy issue. So maybe we will try to email one by one to you. I'll ask my TAs. Hopefully they'll do it maybe, you know, 5 or 10 a day and then do it the next day, something like that. Okay.
Okay.
Yeah. If you have any questions on that, you can get back to me.
Okay.
Fine. All right.
Thank you.
Okay,
Thanks a lot, sir.
guys.
Thank you, sir. Thanks for
Excellent.
getting.
Okay. Excellent. Yeah. Thank
Yeah,
you.
thank you,
Take
sir.
care.
Thank you.
Thank you, sir.
Take care.
Thank you,
Yeah.
sir.
Yeah,
Thank you.
please
Thank you,
keep in
thank you.
touch, sir. Yeah.
Sure, sure. All of you also
Sure.
as well. Come by my office
Sure.
whenever you come.
Sure, sir. Sure. We'll
Yeah, yeah,
come,
yeah.
sir. Thank you, sir. Thank you.
Excellent. Thank you. Thank you. Take care. Bye bye. All the best. Yeah. Yeah. Bye.
Thank you, sir.
Thank you. Bye.
Thank you, sir.
Thank you.
Thank you so much, Professor, sir.
Thank you. Thank you very much.
Thank you, sir.
Thank you, Satish Kumar.